Hello everybody and welcome to my YouTube channel. Today I have an amazing trigonometric identity for you to prove. I personally had not seen this identity before, and the first time I saw it, it sounded cool, but yeah, I was just wondering how can I prove this identity. So before I unravel the problem for you guys, please make sure that you subscribe to my channel and like this video if you will like it, because this is going to help my channel grow, and this is going to help me reach to more people like you, and that encourages me to create more videos, more content like this. So let's jump right in. So we already know a formula for cosine of 3 theta, which is basically 4 cosine 3 of theta minus 3 cosine of theta. And this formula on the right side, it doesn't look like this, even though if you start multiplying this parenthesis perhaps you will reach to some cubic versions of cosine of theta, but yeah, still they are kind of different. So how can I solve this problem? So I will tell you how I solve this problem. I basically leveraged complex analysis, the famous Euler formula, to solve this problem. And this is how it is done. So we know that e to the power of I alpha, this is e cosine of alpha plus I sine of alpha, right? This is the famous Euler formula, and this gives me cosine of alpha to be e to the power of I alpha plus e to the power of minus I alpha divided by 2, right? So here I'm gonna just replace alpha with 3 theta because it can be any angle. So therefore I will get cosine of 3 theta is equal to e to the power of I 3 theta plus e to the power of minus I 3 theta divided by 2, right? And if I want to reach to this expression, I just multiply both sides by 2 and add a 1. Therefore, I will get, the following. So 2 cosine of 3 theta plus 1, it will be equal to e to the power of I 3 theta plus e to the power of minus I 3 theta plus 1. And now probably you're just wondering, how can I turn this guy to this guy on the right? Well, you will see about it. So in the next step, what I will do is to define a new variable. And the new variable basically is a complex variable. I take e to the power of I theta to be a complex number. I call it z. Therefore, the expression on the right will be written as z to the power of 3 plus z to the power of minus 3 plus 1. Very easy, right? And the next step, what I will do is to factorize z to the power of minus 3, and this will produce z to the power of 6 plus z to the power of 3 plus 1. This is also very easy. You can verify that. So now I have this guy. And so next step for me will be to kind of factorize this expression on the right. And the way I'm going to do it, so you guys know that actually we have an algebraic identity, which is basically written a to the power of 3 minus 1. This is equal to a minus 1 times a2 plus a plus 1, right? So we know this algebraic identity is very famous. So instead of z3, let us just take, for example, omega. Or, this is w, but let's take omega. So then I will get basically w or omega 2 plus omega plus 1, which is very similar actually to the second expression here, which suggests that all I need to do is to basically multiply the numerator and the denominator by something like omega minus 1. And then it can be written as this guy here. So therefore, I have 2 cosine of 3 theta plus 1. This is equal to z to the power of minus 3 divided by omega minus 1, which is basically z3 minus 1 times z3 minus 1, because I multiply the numerator and the denominator both by this factor, and times z6 plus z3 plus 1. But according to this identity, algebraic identity, which I put in the rectangle for you, this can be written as z to the power of minus 3 times z 3 to the power of 3, which is basically z9 minus 1 divided by z3 minus 1. And now you're just wondering again, why am I doing all of this? Because if I put this guy equal to 0 on the right side, so I can actually find the roots of this equation a lot easier, because I have an expression such as z to the power of 9 minus 1. And we know that if I have an algebraic expression such as f of z, and I put this equal to 0, and I found the roots, let's say the roots are, this is an order of 9 equation, so these roots are z1 all the way to z9, then algebraic equation f of z can be written as z minus z1 all the way to z minus z9, if basically the coefficient of z to the power of 9 is 1, which is the case here, by the way. So that's why I want to put it equal to 0, not to solve that equation, but simply to find the factors, okay? So let us just do that. And we have to be very careful, because the denominator also will produce some zeros, and we have to exclude them. So let us just go ahead and write z to the power of 9 minus 1 equals 0. So because z was e to the power of I theta, you remember that? So we have basically e to the power of I 9 theta equals 0, which in complex number realm can be written as e to the power of I2 kp, by the way. And as a result, what I will get from this is that basically theta is equal to 2 kp over 9, and k belongs to z, and because this equation is of order 9, it means that I have 9 roots, but I have to exclude the roots of the denominator. So before I find all the roots by varying k belongs to z, let us first find the roots of denominators so that we can exclude them. So z3 minus 1 equals 0. And if I proceed like what I did here, so e to the power of I3 theta equals e to the power of I2 k prime p. So this gives me basically theta equals 2k prime p over 3. I put it k prime so that you do not confuse it with basically k. So we have this here. So we know that actually some of the roots to this guy here, to this equation, can be equal to the sum of the roots to this guy. So we have to exclude them. So the way I'm going to find those is basically to put this 2kp over 9 equal to 2k prime p over 3. So as a result, I will get basically k equals 3k prime. So the roots of the denominator here will be basically theta 1 is 0, and k prime, if you put k prime 0 and k prime 1 and k prime 2, then you get basically 0 and 2 pi over 3, and also you get 4 pi over 3. So these cannot exist in the numerator equation here. So, and I know that basically k, at those k's where I have k equals 3k prime, I have to cancel those k's. So let's go back to this equation here, the equation of order 9. So you remember basically theta there was 2k pi over 9, and typically you would go from k from 0 with k from 0 to basically 8. So what you do here instead, you try to exclude the k's which are basically equal to 3k prime, and that would be k equals 0, k equals 3 times basically 1, which is basically 3, and k equals 6. So I have to exclude those guys. What is remained for me is basically 1, 2, 4, 5, and 7, and 8. So these are basically 6 different values for k, which kind of makes sense because originally this expression here, it was an expression of order 6. So it can have maximum 6 roots. So let's find those roots now. So by the way, in order to not get lost in the whole process, what I will do is basically I will write this equation here. So far I will rewrite it. So we have 2 cosine of 3 theta plus 1. This was equal to z to the power of minus 3 times z6 plus z3 plus 1, if you remember. And now I have found the roots to this equation here. And all I need to do is put these thetas for e to the power of I theta. So basically this gives me, if you put k equals 1, what you will get, so 1 theta will be 2 pi over 9, and then 4 pi over 9, and then you have 3, well, let's just write them down, okay? We don't need to do that here. So we have basically e to the power of I 2 pi over 9, and then we have e to the power of I 4 pi over 9, then we have e to the power of I 8 pi over 9, then we have e to the power of I 10 pi over 9, then we have e to the power of I 14 pi over 9. These are 5 roots, and then we have e to the power of I 8, 16 pi over 9. So we found all the roots. So next step, what I will do is basically I write this 2 cosine of 3 theta plus 1. This is equal to z to the power of minus 3. So this is basically z minus z1 times z minus z2 all the way to z minus z6. And z1, z2, and z6 are basically all these guys here. But what you have to pay attention here is that these roots are complex conjugates. So you know what a complex conjugate is, number is. Basically, if I have z1 equals x plus iy, the complex conjugate value of z1, which I denote as z1 bar, is basically x minus iy. And I have this nice property that if I multiply these two guys with each other, what I will get is basically x2 plus y2, which is basically the same as the absolute value of every one of them. Here, absolute value of z1 to the power of 2. This is the Pythagorean theorem, okay? So here, if you pay attention to this first guy and the last guy here, they are complex conjugate. It's not really difficult to prove because, for example, I proved the first case, but the rest are the same. I have, let's say, z1 is equal to e to the power of I, 2 pi over 9, and basically this can be written as e to the power of, and then, sorry, let me rewrite this again. So z1 equal to e is equal to the e to the power of I 2 pi over 9, and this will be basically cosine of 2 pi over 9 plus I sine of 2 pi over 9, right? So what is the complex conjugate value of this? So it will be, according to this definition, it will be cosine of 2 pi over 9 minus I sine of 2 pi over 9, right? But as a matter of fact, what we can do is to write this in a different way. And that is basically, we can say this is equal to cosine of 2 pi minus 2 pi over 9, okay? Because we know that cosine of generally alpha is equal to cosine of 2 pi minus alpha. In trigonometry, this relationship exists. And this is basically, we take minus to the inside the sign. So this is plus I sine of minus 2 pi over 9. And then I also can actually add a 2 pi there, which basically it gives me cosine of 16 here, pi over 9, plus I sine of, we can add 2 pi to this angle. So that gives me 2 pi minus 2 pi over 9, which again, it gives me cosine of 16 pi over 9 plus I sine of 16 pi over 9. But this is nothing but e to the power of I 16 pi over 9. So in other words, this guy here is the complex conjugate of this guy. So this is very good news. You will see why. And the sum of the angles basically are 2 pi. And as you can see, this guy here is also complex conjugate value of this, and this is also complex conjugate value of this guy here. So how does it help me? Because in the next step, I can write 2 cosine of 3 theta plus 1. Basically, this is equal to z to the power of minus 3 times z minus z1 times z minus z1 bar, because I know z6 is basically the sixth root was the complex conjugate value, and I put it next to the first root, and the same z minus z2 times z minus z2 conjugate value, and here also I have z minus z3 times z minus z3 complex conjugate. So, and the first two parentheses can be simplified in a very nice way, because if you expand that, basically you get z2 minus z1 plus z1 complex conjugate times z plus z1 bar, and the sum of two numbers, complex numbers which are complex conjugates, is basically this here is basically x, right? So what I will get here is this is equal to z2 minus, but let's just pay attention to what these roots are. These roots are basically on the unit circle in the complex plane. So all of them have an absolute value of 1. And what this means is that basically here z1 plus z1 bar is nothing but 2 cosine of 2 pi over 9. Okay, if you just add them, this is what you will get, because z1 actually was this first value here. So it means that this is z2 minus 2 cosine of 2 pi over 9, and the absolute value of it is 1. So this can be very easily simplified. So it means I can write 2 cosine of 3 theta plus 1. This is equal to z to the power of minus 3 times z2 minus 2 cosine of 2 pi over 9 plus 1 times z2 minus 2 cosine of, let's take a look at the second root and also the third root, 4 pi and 8 pi. So there I will have 4 pi over 9 plus 1 times z2 minus 2 cosine of 8 pi over 9 plus 1. And you can already see the terms which existed in the identity are appearing here. And now I just need to further simplify that. So I have this ugly z to the power of minus 3 here, which somehow I have to get rid of. And I have 3 parentheses. As you can imagine, I can give z to the power of minus 1 to each one of these parentheses and kind of make that z to the power of minus 3 disappear. And this is what I will do next. So then I will get basically multiply z to the power of minus 1 to each one of these parentheses. Then you get z plus 1 over, or yeah, z to the power of minus 1. Z plus, yeah, sorry, here I have actually this z term. I forgot to write it. Minus 2 cosine of, also here. Sorry for my mistake. So I have basically that to minus 2 cosine of 2 pi over 9 times z plus z to the power of minus 1 minus 2 cosine of 4 pi over 9 times z plus z to the power of minus 1 minus 2 cosine of 8 pi over 9. Okay? So this is what I will get, and also z plus z to the power of minus 1 can be easily simplified, because this is e to the power of I theta plus e to the power of minus I theta, which is basically 2 cosine of theta, right? Very easy, because that was basically the definition of z. It was e to the power of I theta. So then I get basically 2 cosine of 3 theta plus 1. This is equal to basically each parenthesis. You can factor in each parenthesis, you can factorize 2. Then you get 2 to the power of 3 times cosine of theta minus cosine of 2 pi over 9 times cosine of theta minus cosine of 4 pi over 9 times basically cosine of theta minus cosine of 8 pi over 9. And to the power of 2 to the power of 3 is basically 8. Okay? And this was precisely what we had in the beginning. If I go back all the way up here, so this is exactly the same identity. But so you learned how to beautifully prove this, but actually you can also draw very interesting conclusions from this, because what happens, by the way, pi over 9 is basically 20 degrees, right? So what happens if I put, for example, theta is 90 degrees? So see, you get basically on the left side, you get 2 cosine of 270, which is 0. So you get 1 is equal to 8 times cosine of 90 is also 0. Basically 0 minus cosine of 4t times 0 minus cosine of 80 degrees times 0 minus cosine of so 8 times this is basically 160, and then you have this minus in all of them. So basically this is minus 8 cosine of 40 cosine of 80. Then cosine of 116 basically can be written as minus 1 cosine of, or just minus cosine of 20 degrees. Okay, so minus, it will cancel each other. So basically you get cosine of 20 degrees times cosine of 40 degrees times cosine of 80 degrees. This is nothing but 1 over 8. Very cool results. I'm sure that you can prove this last identity with the help of other trigonometric identities as well, but this is just one way. All in all, this identity is very beautiful. I really like it, but this showcases how you can leverage complex analysis to prove beautiful identities in trigonometry. I personally really love this method. I have used it for proving identities, for solving trigonometric equations in the past on my channel, And you can also learn this method and apply to your problems whenever it is possible. So if you like this video, please again make sure that you like my video and you subscribe to my channel so that you will stay updated on all my contents. And again, thank you very much for your support. This means a lot to me. And see you next time for another challenging problem.